Welcome to a new microeconomics video lesson in this section regarding to game theory. With this video, we continue studying games with incomplete information. In this case, we will learn how to solve static Bayesian games, that is, how to find what we will call the Bayesian Nash equilibrium or solution of these games. As seen in the previous video, static games of incomplete information are characterized by at least one player having different types, while the other players are uncertain about which type their rival actually is. Once the types of each player have been defined and the game has been represented, the next step is to look for the best responses of each player with incomplete information in order to predict the outcome or equilibrium of the Bayesian game. Compared with the notion of best response used in complete information games, there are two main differences here. On one side, the player with incomplete information must choose as a best response the strategy that maximizes expected utility instead of actual utility. Because this player faces uncertainty over different outcomes due to not observing some private information of the opponents, the best response will depend on the player's type. That is, a player with private information can choose different strategies depending on which type they are. And their strategies may differ across at least two of their types, so there is an optimal response for each different type of the player. Once the best responses for each player are known, the next step, as in complete information games, is to find out the Nash equilibrium. In this case, we will call the Bayesian Nash equilibrium, defined as the set of strategies under incomplete information that are mutual best responses for every player given their rivals' strategies. As with other equilibria, in a two-player game, the equilibrium is a pair of strategies that are mutual best responses, so that no player has an incentive to deviate from the strategy chosen in that equilibrium. To find the Bayesian Nash equilibrium, the first step to do is to list all the strategies of each player, bearing in mind that players with private information, those who have types, will have a different strategy for each likely type. Then the second step is to represent the matrix of the game with as many rows and columns as strategies each player has. To fill in the payoffs in each cell, note that the player with incomplete information must compute expected utility in each situation, and the player with private information can have in each cell as many payoff values as likely types, or can calculate again his or her expected utility. From there, the same golden rule used with complete information can be applied. Look for each player's best responses by rows and columns, remembering that the player with private information can have as many best responses as types. Finally, the Bayesian Nash equilibrium will be the pair or pairs of strategies that are simultaneously best responses for all players at the same time. Let us now see all of the above by solving the following example of a Bayesian game. For simplicity, we will always start with the player who has incomplete information. In this example, it is player 2, since he doesn't know the true value of the parameter x, that is the type of its opponent. This player has only two likely strategies, L and R, because it cannot condition its strategies on any type. By contrast, player 1 observes its own type, the realization of X, and can therefore condition its strategies on each type. So in this example, it has four likely strategies: playing U regardless of its type, playing D regardless of its type, or alternate between U and D depending on its type. Therefore, the matrix represented in this game has 2 columns and 4 rows. The next step is to fill in the cells of the matrix, for which there are 2 different approaches that lead to the same final equilibrium. The first approach is, as described in the previous slide, that player 1 has in each cell 1 payoff for each type. The payoff in each type is x equal to 10, and the payoff in each type is x equal to 12 in this example. And then the expected utility in each cell is calculated for the player facing uncertainty, player 2 in this example. The other approach, easier, is to directly calculate the expected utility for both players in each cell, which in this example yields the following matrix of expected payoffs. From here, the same golden rule used in complete information games will be applied to look for each player's best responses. In this case, if player 2 plays L, player 1's best response will be to play UU because 16 is the highest payoff in that column. Whereas if player 2 plays R, player 1's best response is to play the D because 10 is his or her highest payoff in that column. In a similar way, if player 1 plays UU, player 2's best response is to play L, earning 17. If player 1 plays U and D, the best response for player 2 will be R. If player 1 plays D and U, the best response for player 2 is R. And finally, if player 1 plays D and D, the best response for player 2 will be again playing R. We can see that there are no dominant strategies for any player in this game, so there is no dominant strategy equilibrium. However, there are 2 Bayesian-Nash equilibria. That player 1 chooses W and player 2 chooses L, and player 1 playing double D and player 2 playing R. That is one equilibrium where player 1 plays U regardless of its type and player 2 plays L, and another where player 1 plays D regardless of its type and player 2 plays R.